Let us finish our tutorials on substitution with substitution part 3. Here we have m is equal to 20 and n is equal to 48. We also have the expression t is equal to the square root of 5m. As a matter of fact, the square root of all of 5m over 12n. Here we have the template written, and we have right here and here pairs of brackets that are empty, representing the variable m and the variable n. These slots are empty because we will substitute the particular values of m and n into the expression. M is equal to 20, and the blank slot that is left there by n, we place 48 right there. Because of the square root, I have chosen to rewrite the denominator in a form that is suitable for finding the square root mentally. Therefore, I am making use of the fact, or not turning a blind eye on the fact that we have to find the square root in the end. And we are using such a consciousness in helping us to determine how we progress in solving the problem. So we are actually making use of the fact that we are finding the square root and using that as a determining factor in how we progress, and as a matter of fact, how we write the denominator. And we are rewriting the denominator, rewriting the 12 right there, and the 48 we write as 4 times 12. Now, because of writing the denominator in the form 12 times 4 times 12, we may make use of the fact that the square root of 12 times 12, which is what we have right here, and we will discuss this a little bit further on a subsequent slide. So we have these two occurrences of 12. We are taking them together, finding the square root of 12 times 12, which is equal to 12. And also finding the square root of 4, which is by no means steep. The square root of 4 is equal to 2. And in the numerator, we have 100. The square root of 100 is equal to 10. Therefore, we have square root of 100 is 10. Square root of 12 times 12 is 12. And the square root of 4 is 2. All we need to do right here is reduce that fraction by the common factor of 2. And especially the denominator is very simple to reduce by the common factor of 2, because we have it written, or we may say already, with a factor of 2. Therefore, all we need to do is eliminate that factor of 2. Also, in the numerator, we will divide 10 by 2. So, in the denominator, we have 12 times 2. Divide 12 times 2 by 2, and the result is just 12. Also, in the numerator, we will have 2 into 10 is equal to 5. So the result is 5/12. In the denominator of the fraction, we have 12 times 4 times 12, which is equal to 576. For quite a few candidates, it might not be so easy to see that the square root of 576 is 24. One may want to attempt it with the calculator, but as soon as the calculator is in hand, the most likely thing is to go to the entire square root. That will give a decimal result that does not look as simple as 5/12. And as a matter of fact, the decimal equivalent of 5/12 is 0.416 with the 6 recurring. And that will be the actual value if we should attempt to use our calculator to find the square root of the entire thing that we have right here. And as a matter of fact, with the 6's recurring, that should not look as simple as 5/12. One may therefore be tempted to think that the square root might not have been easily found. Therefore, if you take your calculator, find the square root of the entire expression that we have right there, then the result will be 0.416 and the 6 will be recurring. Therefore, it will not be easy for you to see using that calculator, based on the result that you get, that the square root of the arithmetic expression that we have right there may be easily found. Therefore, I have not attempted to go the route of multiplying 12 by 4 by 12 to give 576. As a matter of fact, I've taken the opportunity to see that we have 2 occurrences of 12 in the denominator and may therefore find the square root by taking 1 occurrence. If we take a second look at the composition of 12 times 4 times 12, we will realize that it is easy to find the square root of that product. There we have the product and we are taking the square root of it. The square root of 4 should not be a bother because the square root of 4 is equal to 2. What remains is the square root of 12 times 12. There should be no difficulty. Square and square root are opposite. If by squaring a number we multiply 2 occurrences of that number, then the square root should be 1 occurrence. What I'm saying is that if you square 12, it is the same thing as multiplying 12 by 12, multiplying 2 occurrences of 12 together. Therefore, the opposite of square being the square root, if we take the square root of a number that exists in a double factor with 2 occurrences in the same way that we have right here, the square root will be 1 occurrence. The same is true irrespective of the number. So if we have the square root of 2 times 2, then that is equal to 2. Also, the square root of 9 times 9 is also equal to 9. Therefore, in any situation that we have 2 occurrences of the same number being multiplied, the square root is simply a single occurrence. So if we have 9 multiplied by 9, the square root of that is 9. If we have 8 multiplied by 8, the square root of that is 8. It is that very fact that I use when attempting to find the square root of a number without the use of the calculator. Also, I am very quick to see when, I'm saying quick to see when 1, we have 2 or an even number of the same factor in a product of which we are finding the square root. That is the first one that we are quick to see. Well, I am quick to see. I am also quick to see when it is possible to factorize or further factorize a number to give an even number of the same factor in a number of which we are finding the square root, because that will simplify the process. So if we have an even number of factors to the extent that we have factors that are doubled and are repeated in that fashion, then the square root of that number may be easily found without the use of the calculator. Also, if the number exists in such a way that we can factorize that number, that means write the number as a product of factors in such a way that we have an even number of those factors or an even number of the exact same factor, or we may further factorize that number in such a way that we have an even number of the same factor, then that number is a candidate for finding the square root mentally. We may couple that with the fact that the square root of the product is equal to the product of the square roots. This was discussed at length in decimal tutorials. Take the product that was in the denominator of the fraction and make use of the fact that multiplication is commutative. That is, the order in which we multiply numbers does not affect the result. So we have 12 multiplied by 4 multiplied by 12, and we are writing that, shuffling the 12s closer together and giving the 4 a little bit more space on that right hand side, because we are ready to make use of the fact that the square root of a product is equal to the product of the square root. So the product of the square roots is equal to the square root of the product. So there we have it. The square root of 12 times 12 times 4 is equal to the square root of 12 times 12 multiplied by the square root of 4. The square root of a number with 2 occurrences is equal to 1 occurrence, and the square root of 4 is equal to 2. Therefore, the square root of 12 times 12 is 12, and we know already that the number that we square to give 4 is 2. The resulting square root is 24, but we did not bother to go there because we have 10 in the numerator that has a common factor of 2 with 24. So we have 12 times 2, and that is equal to 24. But we did not go to 24 because instead of going up to all the way to 24, we made use of the fact that the numerator is 10 and the denominator is 12 times 2. Reduce that by a common factor of 2, and that is what was done. There is another principle in mathematics that we may apply, namely, go simple before you go difficult, and you might not get to difficult. On the other slide, we will take a look at what that means. Go simple before you go difficult, and you may never, sometimes you will not get to difficult if you progress by making use of that principle. So here we have the product of 2 and 36, and we are dividing that by 9. Everyone knows that the product of 2 and 36 is 72. We also know that 72 divided by 9 is equal to 8. There therefore should be no difficulty either way. That is, whether we simplify or not in this particular case. So because of the fact that we know that 2 times 36 is 72, and we may divide 72 by 9 to give 8 quite easily, it might not make such a difference. However, we may take steps to ensure that in the simplification we do not encounter any other number as large as 36. We will do that by reducing the product by a common factor of 9. So, well, I'm just using this as a demonstration, and I'm not saying that anyone should have difficulty multiplying 2 by 36 to give 72, and then divide 72 by 9 to give 8. I am sure that we should not have any such difficulty. However, I am saying by principle we should see when we may be able to simplify the expression first. And what are we doing? We are saying 9 into 9 is 1, and 9 into 36 is 4. So 2 4 is 8. So right there and then we did not have to use 72, and we did not have any further encounter with a number as large as 36. Therefore, if we choose to go simple first, we may never be required to go or to use or to manipulate a number that is larger than any number that we have here. But if we choose to go large first, then we may have some difficulty manipulating those digits, and that has the potential for error or for wasting precious time. No doubt 8 divided by 1 is equal to 8. Now look at this one, 71 multiplied by 51. I am sure that we will want to avoid multiplying 71 by 51 if we can, and surely we can. To multiply 51 by 71 may appear to be a little steep. However, we have a common factor of 17 on both numerator and denominator. Therefore, we may reduce the expression by a common factor of 17. We will therefore reduce the expression by a common factor of 17. 17 divided by 17 is equal to 1, and 51 divided by 17 is equal to 3. It is also very easy to multiply 71 by 3. The mental process is simplified by the fact that we do not have to carry any number. Usually, one of the most difficult things when we are multiplying two numbers or any number of multiplicand by any number of multipliers may be the fact that we have some number to carry. In this particular case, we do not have any number to carry. Therefore, for 71 times 3, we may say 3 times 1 is equal to 3, and without any number to carry, we say 3 times 7 is equal to 21. Therefore, we will have 213, 213. 17 into 17 is 1. 17 into 51 is 3. When we multiply 3 by 71, we get 213. Divide by 1, any number divided by 1 is equal to that same number. That is what I mean by go simple, then difficult, in order that we might not get too difficult. I am sure that I do not need 100 examples to make the point. Go simple by first reducing the expression. We may reduce an equation or fraction by a common factor. This has the potential to prevent us from having to multiply or divide by outrageously large numbers at the end. Therefore, if it is possible for you to reduce, then increase by multiplication, then you should attempt to reduce the fraction first. Always investigate expressions like those in order to find common factors by which you may reduce before you start to multiply all of those very large numbers. The expression that we have there on the left hand side of the equation is a difference of two squares. A difference of two squares. In this particular case, we are given a difference of two squares. X squared minus y squared is equal to 144. We are further given information that x plus y is equal to 9, and we are therefore required to find x minus y. As a matter of fact, the value of x minus y. The expression that we have there on the left hand side of the equation is a difference of two squares. Before making use of the particular features of a difference of two squares, we will take a look at its origin and hence its factors that we see in the second line of the solution. So we have x squared minus y squared. That is a difference of two squares. What we have here is a representation of this exact difference of two squares, and this representation is the factorized form of the difference of two squares that we have right here. Good if we can factorize a difference of two squares, because it is also given in the statement of the problem that one of the factors is equal to 9. Therefore, we are required to find the numerical value of the other one. It is therefore not very difficult, considering that the entire value of the difference of two squares is given as 144. Surely, the synthesis of the difference of two squares is very important, and we will consider that in our presentation, which is the synthesis of the difference of two squares. However, since this is not a tutorial on factorization, we will not labor too much on it. There are more detailed analysis and explanation of the difference of two squares in the instructional material in CXC CSEC Paper 2 Solutions, and also in these tutorials that we are doing right now, and the tutorials will be those on factorization, but we are dealing with substitution at the moment. So let us take a look at the difference of two squares. The difference of two squares, that's what we are taking a look at. And we are saying that mathematics is not only comprised of those things that require you to think a lot, because mathematics is based on, I think that it is summarized by the profiles that we have for the CXC CSEC examination. So the requirements are knowledge, reasoning, and comprehension. And no doubt taking a difference of two squares and its factor is heavily on the, I should think, knowledge portion of the requirements of the CXC CSEC mathematics exams. So mathematics is not only comprised of those things that require you to think a lot. Expressions like the difference of two squares can be factorized by identifying the common factors and writing them down. Understanding the origins of the difference of two squares is key to factorizing the expression. So we have this expression which I am saying is the origin of a difference of two squares, and we are saying this is how we arrive at the expression, the difference of two squares. Expand the brackets by multiplying each term in the first bracket by the term in the second bracket. So we are multiplying each term here by the terms that we have here. And what do? We have a times a is a squared. Then we have a times negative b, and that is negative ab. Then we have b times a, which is ba, and no doubt is the exact same term written in a different way, and we will rewrite it as ab. Also we have b times negative b, and that is equal to negative b squared. The two middle terms are like terms. One has coefficient, those two middle terms, one has coefficient -1 and the other has coefficient +1. They are combined by adding the coefficients. So -1 for this coefficient, +1 for this coefficient. Adding them together, a +1 and a -1, the result is 0. And we have therefore no middle term because they have a cancelling effect on each other. They are what we call additive inverses. Therefore we end up with a squared minus b squared, and the term difference of two squares is self-explanatory. It has two squares, one subtracted from the other. So that is a difference of two squares. Two squares, and we are subtracting one from the other, and we know that the difference in arithmetic is associated with subtraction. We will continue with the difference of two squares. The expression gave the result a plus b, a minus b, that is a plus b, or we may say all of a plus b multiplied by all of a minus b is equal to a squared minus b squared. We are examining factorization. The factors should be the answers, so the expression is more appropriately written in the reverse order. So whereas we have from the factors to the difference of two squares, since we are factorizing, we should have the difference of two squares to the factors, which is what we have right there. By making use of the pattern established in the first example, it should not be difficult to write down the factors of the next expression, which is x squared minus y squared, and that is straightforward, and this is the one that we should remember because we will no doubt have this one in a problem that we will solve in a short while. So a squared minus b squared, a plus b, a minus b. What is there to it? X squared minus x squared, x plus y, x minus y. There we have it. And we may place the x plus y in the first and the x minus y in the second, as we have them right here, or we may have them in the reverse order. Now we are required to factorize this we have here as a difference of two squares, and we factorize that by saying, what is the square root of 36p squared, or what did we square in order to get 36p squared? And that is no doubt 6p. And again, what did we square to give 49q squared? And that is no doubt 7q. And that is all that we are required to do for the factorization of a difference of two squares. Now we have 81t squared minus 1. What do we square to give 81t squared? 9t. And what do we square to give 1? 1. Goes right there. And if we have any more, what do we square to give 25a squared b squared? As a matter of fact, b squared 5ab, and goes right there. And what did we square to give 16c squared d squared? No doubt 4cd. Any more? What did we square to give 1? What did we square to give? 4x squared. No doubt 2x. Goes there. So we are just taking a look at the pattern for the difference of two squares. And as a matter of fact, this is not a lesson or a tutorial on the difference of two squares. Therefore, we will just make light work of what we have here for the difference of two squares, and we will leave it up to the videos on the tutorial that involves the difference of two squares, and also especially the instructional material to make our point more conclusive. Now that we know that a difference of two squares has a factor something plus something, something minus something, then we may go straight ahead and factorize the difference of two squares. The expression on the left hand side that we have right here is a difference of two squares, whose factors we may write down. So let us write down the factors of the difference of two squares that we have right there. X plus y, x minus y. As a matter of fact, we made use of this very example on the previous slide. And additionally, we have that expression equal to 144. Now that we have those factors, we may make our substitution, substituting 9 for x plus y. So where we see x plus y, we replace that with 9. To find the value of x minus y, all we need to do is eliminate 9 from the left hand side by division, keeping the equation balanced by dividing both sides by 9. Keep the equation balanced by dividing both sides by 9. So there we are, dividing both sides by 9. 9 will be eliminated from the left hand side, and on the right hand side we have 144 divided by 9. 9 is eliminated from the left hand side, and on the right hand side 144 divided by 9 is equal to 16. So x minus y is equal to 16 is our result. We are not done with factorization as yet. The expression on the left hand side is a perfect square. In expanding the expression on the left hand side is a perfect square in expanded form. So there we have an expression which is a perfect square in expanded form. And as a matter of fact, we are required to identify that expression as a perfect square if we will have any success in solving the problem. So in order to solve the problem, we need to be able to identify it as such. So let me repeat that. The expression on the left hand side is a perfect square in expanded form. In order to solve the problem, we need to be able to identify it as such. We will take a look at the expansion of the perfect square and its particular features in order to get an understanding of the early step, which is the step of writing this expression in the form of a square. We need to take a look at how we may achieve that, or a reason why we might be able to do that. The composition of the perfect square is very important. We will consider that in our presentation. However, since this is not a tutorial on factorization, we will not labor too much on it. There are more detailed analysis and explanation of the perfect square in the instructional materials. Apart from that, there is nothing much to write home about. Therefore, if we want some more or graphic or detailed explanation and so on the perfect square, we may go into the instructional material where we take a look at the fundamental principles involved in writing an expression, the one that we have on the right hand side, in the form of the one that we have on the left hand side, or vice versa. For the purpose of tutorials, we will be more in the region of application than explanation. But there is no doubt that we will continue to make use of the perfect square in the tutorial, and as we said before, more in the form of application than explanation. The perfect square. The expansion of the perfect square has a very interesting result and is frequently used in algebra. Here we are making use of it in a tutorial on substitution. It is important to be able to use the pattern to write down the expansion of any perfect square and to be able to identify the perfect square and write it in its factorized form. And just by looking at the form, we might be able to develop the skill in writing one as the other or in the reverse order. Now we have a perfect square, no doubt. If we have a plus b all squared, that will be equal to a plus b multiplied by all of a plus b. Expand the brackets by multiplying each term in the first bracket by the terms in the second one. So take a plus b here, take each one, multiply by this one and this one, then take this one, multiply by this one and this one. So a times a is a squared. A times b is equal to ab. B times a is equal to ba. A. AB and BA are like terms. Therefore, we may write one exactly as the other, and we are choosing to write the letters involved in that term in alphabetical order. Then B times B is B squared. The two middle terms are like terms. Both coefficients are equal to 1. Adding the coefficients gives a result of 2. The middle term will therefore be 2AB. So we have AB plus AB is equal to 2AB. Coefficient here is 1. Coefficient here is 1. 1 plus 1 is equal to 2. So we have finally that A plus B all squared, which is our initial expression, is equal to A squared plus 2AB plus B squared. The expansion of the perfect square has three terms. The first term is the square of the first term in the brackets. The middle term is twice the product of the two terms in the brackets. The third term is the square of the second term in the brackets. So we have A plus B all squared. We square the first term, which is this term. We square it, the result is A squared. The middle term is 2 times the first times the second. 2 times A times B. That's what we have there, 2AB. And then the final term is the square of B, which is no doubt B squared. So when we have A plus B all squared, it is not A squared plus B squared, but there is a middle term that is equal to the product of the first and the second, and that result will be multiplied by 2 because there are two of them. And do not forget that that is the result of the expansion that we have right here. We will continue taking another short look at the perfect square, and we have right here that we are making use of the initial pattern. So by making use of the initial pattern in the expansion of the perfect square, write down the expansion of the following perfect squares. So we have x minus y all squared. What do? We square the first. Square x, we get x squared. Then we twice the product of the first and the second. The first is x. The second is negative y. So 2 times x times negative y is negative 2xy. And square the second. When we square the second, negative y is squared. A square is always positive. Negative multiplied by negative is positive. So that's it. And this one is the one that we will be making use of when we are taking a look on the slide in which we will be solving the problem. What about that one? Square the first. Square 3a. We square the 3, the result is 9. We square the a, the result is a squared, 9a squared. What about the middle term? Twice the product of the first and the second. 2 times 3a times 4b. So we have 2 times 3a times 4b. So 2, 3, 6 times 4 is 24. So 24ab, and we square the second term. Square 4b squared. The square of 4 is 16, and the square of b is b squared. 1 minus 7t squared. Square 1, we get 1. The second term, which is the middle term, will be twice the product of the first and the second. So there is our 2. There is the first, which is 1, and there is the second, which is negative 7t. And do not forget that when we are taking, we take sine and all, and that will be a negative 14t. And we continue by squaring so square the second term, which will form the third term. Square all of negative 7t. Negative 7 multiplied by negative 7 is equal to a positive 49, and t times t is t squared. So we are just taking a look, just for summarization, that we are able to make use of the perfect square when we get to it. And then what do? Square negative 5t, we have a positive 25t squared. Then 2 times the first times the second. Those two numbers are both negative. Negative multiplied by negative is positive. So that term is also positive, and the square is positive, so the final term will also be positive. Negative 2 all squared is a positive 4. Any other? No other. But we can go straight ahead and solve our problem. There we have x minus y is equal to 16, and x squared plus y squared minus 2xy. That is what we have right here, and I am saying that that expression is a perfect square. Maybe it is not obviously so, but irrespective of how you write that expression, it is still the perfect square, and we have candidates will be able to identify that as a perfect square. As a matter of fact, this expression was on a previous CSEC examination. Therefore, the CSEC examiners expects us to be able to identify this as a perfect square. If they did not expect us to be able to identify this as a perfect square, then we would not have it on an examination paper, because they just don't set problems that they imagine that no one can do. We are accustomed to seeing the 2ab, which is the middle term of the expression or the perfect square, in the middle. Now it is at the end. That does not make it any less a perfect square. Just rearrange the terms. So if we rearrange the terms, we do not have to rearrange the terms, but I am rearranging the terms so that it is more obviously a perfect square. As a matter of fact, I did not rearrange them right here. I did not rearrange them here. So let us do that. So we have x squared minus 2xy plus y squared. There we go. Which is, of course, the exact same expression. And we are saying that we know that this is a perfect square. And what do we write for this one, which is the same as this? X minus y all squared. So x minus y all squared. And I'm sure, here we have it. X minus y is equal to 16. So if you would have forgotten what you did a few seconds ago, then you surely will have some difficulty with the second part of that problem. So we will go straight ahead and make our substitution. So substitute 16 for x minus y. Right. What do? Finish up. From here on, the square of 16 is 256, and that is all there is to it. All that is left is to square 16, and that result is 256. The perfect square was in a bit of a disguise. The examiners know that we are accustomed to seeing the quote-unquote 2ab term in the middle, which is the middle term, the one that is 2 times the product of the two terms. This may be a test of whether or not the perfect square may be identified irrespective of its appearance. And the CXC examiners will just twist it a little bit just to give us a test. And as I said before, this test may be a test of whether or not the perfect square may be identified irrespective of its appearance. And I always encourage my CXC CSEC students to purchase the children's own, because that children newspaper has a puzzle in there sometimes that requires us to find either 7 or 10 differences between two pictures that look exactly alike. And I think that that puzzle is the greatest mathematical puzzle ever designed, because it is a puzzle that is geared at developing your ability to pay attention to detail, especially in the area of taking a look at two things that are, or they appear exactly the same, and to tell the differences between them, which is something that is excellent for anybody who will be able to excel at the subject. And conversely, to take a look at two expressions or whatever they are, and if they look diametrically different, to be able to determine that they are quite similar. We do not have puzzles in the children's own, and I cannot remember seeing any such puzzle, but we are sure that we see the puzzle of the one that I described first just now, the one that requires us to be able to take a look at two things and be able to identify the differences between them if they look exactly alike. And it is now up to our subconscious mind, which is the more powerful of our mental capacities, to help us to be able to do the reverse. Here we have another problem that is quite similar to the one that we have in the portion, the first portion of number 15. Here we have a plus b is equal to 16, and the expression that we need to substitute into is a squared minus b squared. Of course, it will be good if we could factorize a squared minus b squared, writing the factors as a plus b multiplied by all of a minus b. So we have a plus b is equal to 16, we have a squared minus b squared is equal to 96, and we are required to find the value of a minus b, which is quite similar to the one that we have in the first part of problem number 15, and we will take the same steps. The expression on the left hand side is a difference of two squares whose factors we may write down as we have them here and as we said before. All we need to do is substitute 16 for a plus b. To find the value of a minus b, all we need to do is eliminate 16 from that left hand side. Then we will just have on that left hand side a minus b alone, and we will do that by division. We will also keep the equation balanced by dividing both sides by 16. 16 times all of a minus b divided by 16, that will be eliminated from the left hand side, and on the right hand side we will have 96 divided by 16 is equal to 6. So A minus B is equal to 6. Here we have another one that requires that we manipulate the difference of two squares, but this one we will make the double substitution because we do not have the value of the difference of two squares as we had on previous occasions, but we have enough in this particular example to help us to determine the value of that difference of two squares. We have x squared minus y squared, and that is what we are required to find, but we are given the value of the factors. So we have the expression is a difference of two squares whose factors we may write down. So let us write down the two factors of the difference of two squares, and we are accustomed to them. As a matter of fact, we use this exact example for the illustration, explanation of the difference of two squares. So we have no doubt that x squared minus y squared may be written also as x plus y times all of x minus y. Substitute 7 for x plus y and negative 3 for x minus y. So we have x plus y and we have x minus y, and we have the value of x plus y and we have the value of x minus y. So substitute like so. When we have pairs of brackets following each other without any arithmetic operation, the one that we assume is multiplication, and good that we have the brackets there to demonstrate that we are actually multiplying by negative 3 rather than subtracting negative 3. So here we have the useful brackets that we substitute into, and no doubt a demonstration of the fact that we are finding the product of these two numbers. Without the brackets, the expression would look like 7 minus 3, which would have been incorrect. So let us multiply 7 by negative 3, and the result is negative 21. Here we have an expression, as we can see, because we did not just use difference of two squares with the coefficient of the squares being 1. So I am sure that we should not be overpowered by the fact that we have 4p squared and negative 4q squared. The problem basically gives itself away, one might think, because of the difference of two squares that may be factorized to give, because we may factorize this is in the form of a difference of two squares, and we may factorize to give 2p plus 2q as one factor, and the other factor is 2p minus 2q. Why? Because we usually say, what do we square to give 4p squared? 2p, 2p. What do we square to give 4q? 2q, 2q. And of course, one sign in one of the brackets will be positive and the other in the other one will be negative. So we are saying here the problem basically gives itself away, one might think, because of the difference of two squares that may be factorized to give 2p plus q times all of 2p minus q. However, take a look at the information that is given. What is the information that is given? P plus Q is equal to R. What else? From this, we need to arrive at the conclusion that P minus Q is equal to a half. With no coefficient, with the exception of 1 and -1, we are sure that it is not the way that the examiners expect us to factorize the expression. By taking a second look at the expression, we realize that there's a common factor of 4. We may take that common factor first. So we may take out 4 as a common factor first. Why are we taking out 4 as a common factor first? We are taking out 4 as a common factor first because here we have P plus Q is equal to R. The only coefficient is +1 and +1. Here we have P minus Q is equal to a half. The only coefficient here is +1 and the only coefficient here is -1. Therefore, all of the coefficients are equal to 1. We therefore imagine, because of the factors that we have here, with no other coefficient but 1, that these are not the factors that the examiners expect. Because these factors have coefficients of 2 here and 1, 2 here and -2 there. But we are required to make use of factors that have coefficients only equal to 1 and -1. By taking a second look at the expression, we realize that there is a common factor of 4. We may take that common factor first. So take the common factor of 4 first. So we have 4p squared minus 4q squared is equal to 2r. What do? We take out a factor of 4 from the given expression. So take out a factor of 4. If we take this factor of 4 out, we will have 4 times all of p squared minus q squared. I am sure that no one will have any difficulty seeing that this is equal to this, or even worse, that this is equal to this, because if we say 4 times p squared, we get 4p squared, and if we say 4 times -q squared, we get -4q squared. No difficulty. So that is what will happen if we take out a common factor of 4. The expression may be further factorized because I am sure that by now we all should be able to identify a difference of 2 squares and write down its factors. So here, no doubt, p squared minus q squared is a difference of 2 squares. We can identify that as a difference of 2 squares and we can write its factors down. So that will be p plus q, p minus q. Those are the factors of p squared minus q squared. Do not forget that we are maintaining the presence of the 4 that we took as a common factor in our first step. On the next slide, let us make the appropriate substitution and simplify the expression. The expression is an equation. Remember that an equation may be simplified by dividing both sides by a common factor. Go straight ahead. We factorize the expression on the previous slide. Rewrite it here. Rewrite the factors. The 4, the p plus q, the p minus q. All of them will go right there. Then we will substitute r for p plus q. On both sides of the equation, we have a factor of 2r. We may therefore reduce the equation by a common factor of 2r. So we have 4r we have p minus q, and we have 2r. So on both sides of the equation we have a factor of 2r. We may therefore reduce the equation by a common factor of 2r. So 4r divided by 2r is 2, and 2r divided by 2r is 1. So on the left hand side we have 4r divided by 2r, and the result is 2. We will return our p minus q. Then on the other side we have 2r divided by 2r is equal to 1. Goes right there. And what? P minus q is multiplied by 2 on the left hand side. Divide both sides by 2. So after reducing by 2r into 4r is 2, then we return the p minus q factor. Then we say 2r into 2r is equal to 1. We need the value of p minus q. As a matter of fact, we are told already that the value of p minus q is equal to a half, and all we need to do is demonstrate that it is so. So we have p minus q is multiplied by 2 on the left hand side. We need to eliminate that 2, and we will eliminate that 2 that we are multiplying by dividing by 2. Need to keep the equation balanced. Divide by 2 on both sides. Therefore, eliminate the 2 from the left hand side by division, and we will also divide by 2 on the right hand side to keep the equation balanced. Then these 2 will be eliminated, and we have p minus q, and on the right hand side we have a half.